Hi there, thanks for clicking on and watching. Welcome to this video. I'm going to go through some predicted questions for the stats paper for Maths A Level 2023. If you look in the description for this video, so just do the show more drop down arrow, there are chapters included. So if you wanted to go to a particular topic to just watch that particular question, you can use the timestamps in the description. Also in the description is a link if you would like to join me on a live revision workshop. I'm thinking of putting some on the run up to the exam, so please use the link and sign up to get involved. Please do also bear in mind that nobody can actually predict the questions that are going to come up on the paper this summer. I've just selected some questions, a broad range of topics that you can have a look at. They've got some bits and pieces in that do make you think. You are going to be challenged and maybe be asked to think in a way you've not thought about things before on the day. So the more you can practice past paper questions, the better you're going to be prepared. So do not use this video to narrow down topics. Just use it to get a sense of a flavour of what to expect on the day. So let's do some stats questions then, and in this video I'm going to include some questions on the Edexcel large data set which we've got in this question. Also in this question we've got a graph to look at and a table. So picking some questions where you've got some other bits to think about before you can even answer the question. So here we've got a scatter graph. It mentions correlation coefficient here, so this question is about correlation. We've got two variables, daily wind speed against daily pressure. Now in this table, the coefficients here, the intercept means the y-axis intercept, and we have got the gradient. It tells us that the correlation coefficient is minus 0.477, which ties in with the fact that we've got negative correlation, which we can see from the line of best fit sloping downwards. Now these lower and upper 95%, remember that it is the independent variable that is on the x-axis, and you always take readings reading up to the line of best fit and getting the answer on the y-axis. That's when we do a regression line y on x, because we can only take readings that way. So the lower 95% means that we have just use the lower 95% of the daily mean pressure, what's on the x-axis data. So we've cut off the high data, and therefore the y-axis intercept is going to be lower because that slope's going to be reduced. And then similarly going the other way, we will cut off the low data, the bottom 5%. So let's have a look at what they're asking us to do in this question. In part A, we're being asked to state what is measured by the product moment correlation coefficient. That is just the linear association between the two variables. So when you're asked to state something, then that is exam speak that you can just write it down. That's just something that you can learn. In part B, we're asked to comment. So when you're asked to comment, you just say what you see. And what sort of correlation do we have? It is a negative correlation, as opposed to in part C when we're asked to interpret. So when you're asked to interpret, you are the expert and you've got to relay that information into layman's terms. What does the interpretation of the correlation between the two variables mean in terms of these variables? Well, as the daily mean pressure increases, then the daily wind speed increases, then daily wind speed will decrease. So that is negative correlation. As one goes up, the other goes down, will decrease. I suppose you should have mean there. Okay, so whenever you're trying to interpret in terms of correlation, you just look what the variables are on the axes. As one goes up, the other goes down. So you could write that the other way around, but I've just written it that way for now. Okay, in part D, test at the 5% significance level whether or not the product moment correlation coefficient for this population is less than 0. State your hypotheses. So our H0, our null hypothesis for correlation coefficients, the population correlation coefficient is rho, and that is always the default position for the null hypothesis is that it's 0, meaning that there's no correlation. And then our alternative hypothesis from the wording of this question is that it is less than 0. And then we can have a look at this here, which is the p-value. Now the p-value is the probability of observing a non-zero correlation coefficient given that we've assumed that the null hypothesis is true. So the probability of that happening here we can see is very low. The p-value is less than 0.001, which as a percentage is less than 0.1%. Well, we only need to be less than 5%. So as the p-value is less than the 0.001, it is also less than 5% because it's even less than 0.01%. So that is telling us there is evidence to reject H0 and conclude there is negative correlation. I'm in that space here, negative correlation. Okay, part E, write down the regression model. So this means just write down the regression line. So the regression line, well, we've got the y-axis intercept of 180. So in terms of y equals mx plus c, y is equal to, now when you're doing the regression line, you have the y-axis intercept first. It's 180 minus the gradient, which is minus 0.1694 x. But in terms of what's on the axes, the wind speed is on the y-axis, so we can say w is equal to 180 minus the 0.1694 p, the pressure. F, interpret the gradient of the line. Well, with the gradient of the line we know is the 0.1694, but what does that mean? If we looked at the gradient, so if I draw a little triangle gradient, it means for every 0.1694 decrease in wind speed, then the daily mean pressure will increase by 1. In order for me to have a gradient of minus 0.1694, you'd have 0.1694 divided by 1. When you're doing gradient, you have to have rise over run, so you can just put a 1 on the bottom, which means for every 1 along whatever's on the x-axis, then the fall on the y-axis, because we've got negative, is going to just be that value of the gradient. So we can look at the axes and say that these aren't really measured in terms of decimals. We could just times that by 10 and times that by 10 and say for every 10 increase in the pressure, then the wind speed is going to go down by 1.694 or 1.7. So again, when you're interpreting, you're putting it into layman's terms and just explaining to somebody what that means in terms of the variables. Now, part G, the regression model was used to predict the daily wind speed of 11.15 for a daily mean pressure of 9.95. So 9.95 is going here, and we're reading across and getting that 11.15. And it's asking us to comment about the accuracy of this prediction. Well, we do have some data at this level where we're reading from. We can see the line of best fit just fits the data, but there aren't many data items at this level. So most of our data items are here in the middle. That would be much more reliable to take a reading there. So commenting here, I mean, it is reliable because we're not extrapolating, but it's not going to be that accurate because we don't have many data readings at that end of the data. Now you might be wondering when I've just gone across there that the y-axis intercept looks like it's about 11 here. But did you notice on the scale on the y-axis goes from 0, but here the x-axis goes from 990 to 1000. So that space there is only a space of 10. And of course we've got lots of data here. The x-axis has been all squashed up. So if we did extrapolate that line of best fit, by the time we went all the way back to where the y-axis would sit, we would get a y-axis intercept of that 180. This next question is telling us that the heights of a population of men are normally distributed, and we've got mean, mu and sigma. We're being asked to find both of those, so two unknowns, we need to solve them simultaneously, and in order to get two equations we need two bits of information. We've got that it's known that 20% of the men are taller than 180 and 5% are shorter than 170. So part A is asking us to sketch that on a diagram. So we need our bell-shaped normal curve. So 20% of the men are taller than 180 and 5% are shorter than 170. Now in part B we've got to find mu and sigma. So what we need to do is put that information onto the standard normal, and using this information here from the formula book, you've got your percentage points from the normal distribution, and in order to have here the 20%, which is a probability, we look here the 20%, the p-value as a decimal gives us a z value, which is on the x-axis of 0.8416. Then looking for the 5% here, we need to go here. Now the percentage points are all positive. That means they're to the right of the mean. The mean when we've got the z normal being 0, but because we are now to the left, because of the information telling us it's the shorter, this has to be minus 1.6449. So just taking the minus value of that z value. So now we can write two equations using the formula that z, which is the x-axis answer, is equal to x minus mu all over sigma. So if we write 0.8416, the z value is the x. The corresponding x value in that position is 180 minus mu all over sigma. Cross multiply 0.8416. Sigma is equal to 180 minus mu. And just take that mu over 0.8416 sigma plus mu is equal to 180. Now if we do the same thing with the minus one, so minus 1.6449 is equal to 170 minus mu over sigma. Cross multiply again, and we can see that if I write them underneath each other, I'm going to get minus 1.6449 sigma plus mu is equal to 170. So what we're looking for when we're solving simultaneous equations is one of the variables to be the same and the signs are the same, so we're going to take away. So if we take away in this direction, you're going to get 2.4865 sigma is equal to 10, and just divide brings out that sigma, the standard deviation, is 4.021. Now if you sub that back in, you'll get that mu is 176.6. So that's part B, 7 marks for doing all that. And then in part C, 3 men are selected. Find the probability that they are all taller than 175. So now we know what mu and sigma is, normally distributed with 176.6 and the 4.021. What is the probability of X being bigger than 175? Now, if you work that out on your calculator, that's the probability of just one man being taller than 175. And that comes in, when you feed it into your calculator, you'll need to put a lower limit of 175 and then just choose an upper limit, say 1,000, 10,000, and then feed in these values. On your calculator, you get 0.6567. Now what I did is left these answers from my simultaneous equations to more decimal places to get a better answer there. But then the question's asking us to get 3 men, so I want the first man and the second and the third. And what does that word mean in terms of probability? And means multiply, so the probability for 3 men is going to just be that probability that we've worked out for 1 man times by itself 3 times, so that's going to be cubed. And if you do that on your calculator, it comes out to be 0.282. Next, I've got another question that involves the large data set from Edexcel. We've got Kyang and Maggie. They're studying the pattern of rainfall and they live in Herne, one of the places where there's the weather station. Kyang decides to record whether or not it's raining at 6 a.m. for the next 10 days. State the method of sampling. Well, this is going to be opportunity sampling because she is recording the rainfall at the same time every day. Okay, part B, Kyang suggests that the binomial distribution with n equals 10 would be a good model. Explain why the binomial distribution might not be a good model. So for this, we've got to think about using the binomial. It's either going to rain or it doesn't, so that kind of fits. Small number of trials, that fits. But what's wrong here is that consecutive days might not be independent. So let's just write this. Consecutive days may not be independent. So the rain, the current rain on one day is going to have an effect on the rain on the next day. Okay, next bit, Maggie uses data from the large data set in Herne 2015, selects 30 days, and some of her 30 days have this TR. Well, TR stands for trace, and that is less than 0.05 millimeters of rain. Suggest what Maggie could do with these TR entries. She could use 0 instead. So when she's going to do her calculations, she could just put in nothing because it's so small. She can just put in 0. Explain what effect this is likely to have on the estimate for the mean. It's likely to be an underestimate because she has set them all to 0 and there is a small trace, so it's likely to be higher than her estimate when she uses 0. For the rest of this question, we're still looking at Maggie, who has summarised the 30 days in this grouped frequency table here when she's collected the data on total rainfall. And we can see if there were any days that had trace, they would be included in this section here because there's 7 days with no rainfall and so on. So we're using this information to estimate the mean for part D. So in order to estimate the mean, we need midpoints. So halfway between 0 and 1 is going to be 0.5, and the next one's going to be 2, and then 5, and then 11. Yep. And what we need to do is add up all the rainfall and divide by how many we have. Well, it was 30 days. We can see that if we add up the frequency. But if we presume on 10 of the days they had it in the middle of the group, and this is why it's an estimate, we're going to have to add all of them up. Well, we can include this one here, but it doesn't really make any difference. 0 times 7 plus 10 times the half plus 2 days where there was 2 rainfall, 2 millimeters, plus 7 days when there was 5, plus 4 days when there was 11. So that sum would add up all the rainfall, and then if we divide by 30, this is 88 over 30, which comes to 2.93. So that's part D. Part E, show that the estimated value of SXX, which is the sum of the squares, so that's the value that you can use before you find the average as how far each of the data items lie away from the mean. So it's used to calculate the variance, and it is the sum of the squares. So I've put over here the section of the formula sheet where you can see how to calculate the sum of the squares. So it's just how far does each of the data items lie away from the mean, and then you square them. But we can use this version of the way to calculate it by doing the sum of the squares. So this is the thing that we need to square, and then we've got 10 of them. So you need to do 10 times 0.5 squared plus 2 times 2 squared plus 7 times 5 squared plus 4 times 11 squared. That will give you the sum of the squares, and that comes to 669.5. And then for the rest of the calculation, we need to do 669.5 take away. And this bit here is the sum of the x's all squared. Well, the sum of the x's was our 88, so it's 88 squared over 30, and that on your calculator does come to the 411.4. Part F, Maggie defines an outlier as a value which is 3 standard deviations away from the mean. Well, the mean was our 2.93. How are we going to find our standard deviation? When you calculate the SXX, that's the sum of the squares. So the standard deviation is the sum of the squares, the 411.4, divided by 30, finding the average of them, and then taking the square root. And if we do that on our calculator, that comes out to be 3.7. So we need to find 3 standard deviations above the mean. So the mean was 2.93, and if we plus 3 times the standard deviations on, that comes out to be 14.042. And if we do 2.93 minus 3 times the 3.70, that comes out to be minus 8.17. Now anything above or below those two is going to be considered an outlier. So we haven't got any values that are negative, so we've got no outliers at that bottom end. But because we might have some rainfall that goes above the 14.042, then possibly there could be some outliers in that final group. Possible outliers in the 7 to 15 group. Next, we've got a probability question, and we're going to be drawing a Venn diagram just to go through a couple of the rules that you use. Conditional probability, probability of A given B is equal to the probability of A intersection B divided by the probability of B. If we are given that B has happened, then we are restricting what we're out of. It's got to be out of the B on the bottom. And where do those two intersect? If we want A to happen as well, that's the rule that you need to use for conditional probability. And then the other one, we're going to be doing something about independence here. So the probability of A times the probability of B is equal to the probability of A intersection B if we have A and B being independent. So let's have a look at this question here. Then we've got E being 0.25, F being 0.4, and the intersect is 0.12. Now, first thing you should do is draw the Venn diagram and put those on, E and F. Now, the only thing we can fill in straight away is the 0.12 being the intersect, because if we want E to come to 0.25, we'll need to take that off. So all of E's circle does come to 0.25, and that will give us that E is 0.13. If we want to make F circle add to 0.4, need to again take the 0.12 off, and then that will be 0.28. Now, if you just look at F's circle, it all adds to 0.4 plus the E bit, that will be 0.53. So on the outside will be 0.47. Now for part A, we're being asked to find out what the probability of E dash given F dash. You can't really see those dashes, but there are dashes there. So the dash means not E given not F. So this, using the rule here, is going to be the probability where they both intersect divided by the probability of being in F dash. So where does not being in E intersect not being in F? That's going to be the bit here on the outside, so that's 0.47. And the probability of F dash, well, if F is 0.4, then F dash is just 1 minus that, so it's going to be 0.6. So we can write that as 47 over 60, or to 3 significant figures given as a decimal is 0.783. In part B, explain showing you're working whether E and F are statistically independent. Well, using this second rule we just went through, the probability of E times the probability of F is equal to 0.25 times 0.4, which is equal to 0.1. 0.1 does not equal 0.12. Therefore, they're not statistically independent. So that's all we need to do for that one. Now we've got a new event. G is 0.15, and we're told that E and G are mutually exclusive. That means that there's no intersection. So we can put G here, because there's going to be no intersection with E, because we're told they're mutually exclusive, but we are told that F and G are independent. So the probability of all of F times all of G does equal that intersect in the middle. So we've drawn it on, but we need to fill some values in. So if we're told that they're independent, then the probability of F times the probability of G is equal to the probability of F intersection G. So F 0.4, we're told G in the question is 0.15. If you times them together, that comes to 0.06. So in the intersection bit there on G is 0.06. Now if we want G to come out to be 0.15, we just need to take that away. So the G bit on its own will be 0.09. Now we also need to change F's, because G hasn't got any other probabilities with E, then it's just going to be that bit there needs to lose 0.06, so that's going to be 0.22, and then on the outside, because we've now had an additional 0.09, that one will have to go to 0.38. Now our diagram still adds up to 1, and we've drawn for part C the G included onto the diagram, and now we just need to do part D, find the probability that F union G, and then we've got a dash. So this is going to be the probability of F union G, if we find that first and then do 1 minus it. So F union G is going to be all of F, the 0.04, plus the G bit on its own, 0.09. So that's going to come to 0.49. So the probability of F union G and then dash is going to be 1 minus 0.49, which is 0.51. This next question is a binomial distribution approximation to the normal distribution. The binomial distribution is a discrete distribution, and in part A, it's asking us the conditions under which we can approximate it to the normal distribution. So that can happen when n is large. So when you've got enough trials, then it can merge into a continuous distribution. And also because we've got 2 marks, we've got to say 2 things. P is close to 0.5. So probability of success being 0.5 means probability of failure is also 0.5. So you've got some symmetry there. The binomial distribution will be symmetric, and the better symmetric the binomial distribution is, it's going to be better to approximate it to the normal, because remember, the normal is a symmetric distribution. Now in part B, it's asking us to write down the mean and variance for the normal. So mean is equal to NP. So if I had, for example, 40 trials and the probability of success was a half, how many of those 40 would I expect to come up success? You would do 40 times a half, which is going to be 20. So it's like the relative frequency. When we're trying to find the mean, it's the average amount that we would expect in the trials to come up as success, and we're just going to get that by times in those two together. The variance, which is going to be this measure of spread, is going to be NP and then 1 minus P. So if P is probability of success, 1 minus P is the complement of that, and that's going to be the probability of failure. Now, part C, we're being told that a manufacturer claims that more than 55% of its batteries last for at least 15 hours. Write down a reason why the manufacturer should not justify their claim by testing all of the batteries. Well, if they tested all of their batteries, then they would have them running for more than 15 hours, and that would run all the batteries out, and there would be no batteries left. So that would be a silly idea to do that. No batteries left if we've tested them all. Then in part D, to test the manufacturer's claim, a random sample of 300 batteries were tested. State the hypotheses for a one-tailed test. Well, we can see it's going to be a one-tailed test because the manufacturer is claiming more than 55%, so that's just in one tail. So D, we're going to say that X is binomially distributed with our 300 and our probability of success. Stating our hypotheses, the null hypothesis is that the current state of affairs is we think it's 55% because the manufacturer is claiming that it's bigger than the 55%. So H0 is our default position, what's currently going on, 55%, and H1 is what we think it's going to be different. So we think it's going to be above the 55%. So that's our hypotheses. And then in part E, we're actually asked to carry out the test, but use a normal approximation, because out of the 300, which is a large N, 184 have lasted for 15 hours or more. So if X is binomially distributed and we've got 300 and 0.55, and we can assume H0 is true, so that's on the basis that we think it is 55%. Now we need to use a normal approximation. So because we've used X already, in order to do an approximation, you have to introduce another letter. So Y is going to be normally distributed with NP as our mean. So that will be 300 times the 0.55, and that comes out to 165, and then NP 1 minus P, so the 165 times 0.45 comes out to be 74.2. 0.25. Now we want to be testing the probability of X being bigger or equal to 184. So on the basis that we think H0 is true, we would think 0.55 of the batteries would last, and so 0.55 of 300 is our mean, the 165. On the basis that we think 165 will last more than 15 hours, what's the probability of 184? Now, because we've done a normal approximation, if you think where 184 is, and we're going to be thinking it's bigger than that, in order to do the normal approximation, we need to do a continuity correction and actually test what's the probability of Y being greater than 183.5. Because when you're doing a continuous distribution, you can never have it exactly equal to one discrete value, so you always include a little bit more past the range that you're looking at for the binomial distribution. So now all we need to do is find that probability on our calculators. So in your calculator, put 183.5 as your lower limit, put an arbitrary large number, I always put sort of 10,000 as your upper limit, and then you put in your mean is 165. Remember, your standard deviation has to be the square root of 74.25. So if you do that on your calculator, it comes out to have a probability of 0.0159. So looking at that as a percentage, it's 1.59%, which is less than the 5% significance level. So that's going to be in the critical region. So that is telling us, so we can reject H0. There is evidence to support the manufacturer's claim. Thanks so much for watching. If you're still with me at this point, do like and subscribe if you found the content of this video useful, which I hope you have. Good luck with your revision and your exams this summer if you're sitting them this summer, and I will see you on the next one.